Hi, this is Michael Pfeifer. This is another episode of Metal Conversations. In this episode, I want to talk about successful products. From a purely engineering perspective, what is a successful product? To me, it means that it meets all performance and reliability requirements. It's low cost to produce, meaning the components within the product are low cost to produce, and then the product can be easily assembled together. We meet the development schedule on time and perhaps it's an innovative design, has some aspects of the component designs give improved performance and reliability compared to competitors, or the designs are such that the costs are low cost and provides a competitive advantage compared to competitors' products, or the product performs better than competitors' products. Those are all definitions to me from an engineering perspective of what is a successful product. The product might itself not be successful from the perspective of the marketplace accepting it, but that's a separate story because I'm just an engineer. I'm not in marketing. So I'm talking only about the successful product from a purely engineering perspective. To have a successful product, many things have to happen during product development. Hope and luck don't work. And from my perspective, there are many aspects of product design that involve materials engineering decisions, or where materials engineering can have an important part in order to improve the chances of success. And I want to talk specifically about component design and making engineering decisions about component form, that is its shape, dimensions, and features in the component, as well as making decisions about the materials used to make the components. In my experience, what I've found is that many engineering teams overlook engineering the metals used in components, and they end up missing opportunities to optimize components to meet performance and reliability requirements at low cost. And that optimization will often involve making trade-offs between form and materials in order to come to a component that meets the performance and reliability requirements at low cost. And low cost means the materials that are used are low cost and the cost of fabricating components is low. Cost for fabricating components are not low when it's a hassle to fabricate the component, and the people fabricating the component pass that cost back on to the people who are purchasing the component. It can be a hassle to fabricate for a number of reasons, one of which that someone will design a component and select a material that's a hassle to use. For example, if they select a steel alloy that's difficult to machine. So if it's a steel alloy that has a medium amount of carbon in it, and people don't use, let's say, a spheroidization anneal or a full anneal on the steel prior to the machining in order to make it easier to machine. Or maybe they don't specify a rephosphorized steel or resulfurized steel that is easier to machine. And the same concept applies to other methods of fabricating components. And this is when people get quotes from fabricators that are higher than expected, or they'll even get no quoted because it's too much of a hassle to fabricate the component. Cost is also a function of the availability of the material. So we want to optimize the component in order to be able to meet performance and reliability requirements at low cost. So that's one aspect of success. Another aspect of success that I mentioned is meeting the development schedule and launching the product on time. And one thing that gets in the way of meeting development schedules is when the materials selected for a component don't provide the necessary reliability. So the component will be exposed to corrosion conditions or fatigue conditions or high temperatures. And if the materials can't withstand those conditions, then there might be product failures during testing. And when there are product failures during testing, we have to figure out what the failure is due to, and then make new samples and go through testing over again. It's possible during component design to identify tests and carry out tests to evaluate reliability without having to build the entire product, and to understand the effects of different exposure conditions on materials and how the materials degrade, and to figure out what the reliability will be, and to select materials before building the entire product and going through the time and expense of performing product level testing. And then if it fails, having to go through the additional expense and time of additional testing. This materials level testing is part of this materials engineering that I talk about, where we're looking at different materials identifying different materials to use, and figuring out ways to evaluate the effects of stressors on those materials, that is, the use conditions on the materials, and identifying how we'll measure the effects, and then analyzing the materials afterwards. All of those things involve materials engineering. A lot of people overlook that application of materials engineering, pick one material, and hope for the best. And this is especially problematic when people are designing a new product that's an iteration of an old product, but the new product has higher performance requirements or higher reliability requirements. Maybe it's going to be exposed to more aggressive conditions or has to have a longer reliability. And people try to use the same materials as in previous products that had lesser requirements on them. And this can be a problem for trying to pass product level testing. Finally, innovating. Many people are looking for ways to innovate, and they overlook the engineering of the materials used in the product. I've been using the term engineering the materials or engineering the metals. This doesn't have to be a complicated thing, and quite often we're using basic materials to engineer the materials. And it could be simply changing from an alloy that has one level of carbon in it to another alloy that has a different level of carbon in it, and heat treating it in a slightly different way in order to get different properties. Or taking a steel that's heat treated and you're doing the heat treatment in slightly different ways in order to get different properties that enable different performance and reliability. Or just applying a coating to the steel or to whatever other metal is being used, whether it's brass or aluminum. These are all ways to engineer the materials in order to come up with designs that give performance and reliability or improve performance and reliability at lower cost, and designs that are innovative that give your products a competitive advantage. Unfortunately, a lot of people overlook engineering the materials. They focus on form. So why are people overlooking the materials? Well, one of the major reasons is the lack of education about metals engineering, metallurgy, and also materials engineering in general. Most engineers get one class in materials engineering in college. It used to be a long time ago they'd have to take a class in metallurgy. Now it's on all materials, so it covers plastics, ceramics, and metals. And it's taught by professors who might not have practical experience. So it's a one course. It covers a lot of materials, and engineers don't come out with a good understanding of material science and specifically metallurgy. So it's not very realistic to expect them to be able to engineer the materials used in products. And it's the same thing for me. The analogy is, I took one course in electrical engineering in college. And it would be ridiculous for me to go and try to do electrical engineering. I just wouldn't be capable of doing that. I don't have the training, and I don't do it on a day-to-day basis. And I think the same thing applies to metals. And I think for some reason, people, because they're exposed to metals every day, they think that exposure is enough to make metals engineering decisions. A long time ago, a manager from a large corporation that makes products that many of you may be familiar with, and he very flippantly said, was dismissive of materials engineering, saying, we just give our mechanical engineers these 2 handbooks, and they're able to make materials decisions based on these 2 handbooks. That's a really cavalier attitude to take to engineering one aspect of components that can have a critical impact on cost, performance, and reliability. Interestingly, so I think that if people want to be more successful in terms of making products, and also successful with their own time and be more productive and be able to develop products faster and products that are more innovative and products that are less expensive, they should start looking at engineering the materials and becoming more knowledgeable about metals engineering. So I'm offering some resources for learning how to apply metallurgy and metals engineering to design and manufacturing in order to design and produce successful products. So I've got 3 things I'd like to tell you about. First is a short article I recently wrote about the component design process, and it includes considerations for material selection. That article is called Designing Optimized Components. If you go to my website, www.imetllc.com, and look at one of the recent blogs, it's on designing optimized components. The other thing is that on July 6th, I'll be offering a 30-minute course about identifying the stressors, that is, the conditions that cause materials to degrade, and how to evaluate the effects of these stressors without building an entire product. This is kind of doing the metals engineering I discussed for evaluating reliability. And that course is called Design for Reliability. It's also in a recent blog. I discussed that, and you can get information about that in the recent blog. This is just a 30-minute course, and it's also offered through Zoom. And I know people are tired of doing things online, but this is the most effective way to get training across. The course is just 30 minutes, and to try to keep it short so people don't have to spend too much time in front of the computer. It will be recorded so that people can watch it later if they happen to be distracted while watching the live course. I will keep the course engaging and not linger on any points too long so that people will feel compelled to stay with the course. Finally, the Design for Reliability course is part of a new set of short courses that I'm going to be offering. It's called Metallurgy for Successful Products series of short courses. These are 30-minute presentations on a variety of metallurgy and metals engineering topics related to design and manufacturing. The topics include design for reliability, which I already mentioned, fatigue fundamentals, electroplating basics, hydrogen embrittlement, design for manufacturing, and stress corrosion cracking. Each of those individual topics will be its own presentation, be 30 minutes long. You will be much more knowledgeable. You'll have a lot more details about those different topics than you had before. All these topics should be of interest to many engineers. The Metallurgy for Successful Products is mentioned in a recent blog on the website as well. So go to www.imetllc.com to get information about those three different things. If you have any questions or comments about this podcast or about anything else, or if you have ideas for podcasts or short courses or articles, feel free to email me. My email is at mike@imetllc.com. That's it for today's podcast. Thanks for listening. And if you haven't already, subscribe to the Metal Conversations podcast series to receive alerts for when new podcasts are released. You can subscribe on Spotify, Google Podcasts, Apple Podcasts, and all the other podcast outlets that are out there. Thanks again for listening. Good luck with your metals. Bye.